All right, let's get started. So as a reminder, the next thing in many project that you guys have to do is submit a one-page report that's due pretty much in a week. So next Wednesday by midnight. One important thing to remember is not to submit your report till you have made sure you formed your group on Autolab. And there's a bunch of requirements from the PDF what you need to put in there and don't need to put in there. So you can look up the mini project page on the web page. The way I'm going to assign, so if, for example, if there's more than one group who wants to do the same case study, the way it's going to be broken is whoever submits on Autolab first. And so if after you submit a report, you want me to take a quick look just to make sure whether your case study is free or not, you can do that. If not, I will just start grading them starting Thursday next week. Any questions on the mini project report? Forgot your name, sorry.
Kyle.
Kyle.
If we submitted our project and then we realized we didn't make our group and then make it, are we going to have to resubmit it, or do you think that'll be?
If you submit your report before forming group, yes, you have to resubmit it. Okay. The way it works is once you submit as a group, it's created as individual submissions for each of your group members. So that's why you need to form the group before you do it. Any other questions? All right, so we were looking at computing the connected components of a graph. So again, as a reminder, what we did last time was we looked at the correctness of explore algorithm, of which BFS is a special case. And the way what the algorithm outputs is if you start the explore algorithm at vertex S, it will output the connected component of S, which to remind you is a set of all vertices that are connected to S in the graph. Okay. We'll also kind of quickly look at DFS, and we won't kind of walk through in class, but kind of hand wave and argue that DFS is also a special case of the explore algorithm, and hence we have actually already proved the correctness of DFS algorithms. So let's start off with the DFS algorithm. Here is the kind of the simplest recursive statement of the DFS algorithm. And what you do here is it's a recursive algorithm. So let's say the only thing that is shared across the different recursive calls is this: you maintain whether a vertex has been explored or not. So you can do that with a global array, for example. And once you start the DFS of vertex U, the very first thing you do is you mark it as explored. And this set R is what's going to be output as the connected component at the end. So you add that vertex U to R. And then what you do is you look at all neighbors of U. That is, look at all edges which have one endpoint as U and the other endpoint as V. If V is not explored, then you recurse on V. If it's explored, that means you've already looked at it, you just ignore that part. Okay. So, all right, maybe let's kind of want to talk to your friends and convince yourself that this is indeed a special case of the explore algorithm we looked last time. If there are no questions, we'll move on trying to look at other problems related to connected components. Or do you want me to do a run before you guys talk? All right. Examples typically are good. So let me actually run through the algorithm on an example, and then you guys can talk among yourselves and convince yourself that this is a special case of explore. So again, here is just the entire algorithm statement in this box. I'm going to do a run of DFS on this graph. We had seen this graph before for BFS. And we're going to assume that we are starting the run at 1. So I'm going to, the very first call to DFS will be DFS of 1. And so in this case, I'm going to What I'll also do on the right over here is I'm going to create what I'll call a DFS tree. This is kind of the analog of the DFS tree as we go along. Green node denotes that the recursive, the program is at the recursive call at the green node. And once it's explode, I'm going to mark it as red. Okay. So it starts off with 1, marks it as red, then it has 2 neighbors, 2 and 3, and the DFS doesn't specify which order you pick them in. So in this case, let's say I pick 2. So since you went to 2 via 1, you add in the edge from 1 to 2 in your DFS tree. The next thing you do is you mark 2 as explode, and then you go to the next neighbor of 2. So you look at neighbors of 2, then it could, 1 is a neighbor, but the point is it's already explode, so you're not going to go there. So let's say the next one that you go to is 4. You again add this edge from 2 to 4 in this tree. Then 4's explode, you go to the next neighbor of 4 that's not explode, which in this case is 5. So the recursion goes to 5, then 5's explode. You look at the neighbors of 5 that you can go to, it's either 3 or 6. Oh, sorry, you add the edge from 4 to 5. Then say you go to 6. Okay, and then you mark it as explode. Explode, not explode. What's going to happen next? Alex.
Look back at 5 and see what.
Okay, let's just one step. Yeah. So the point is now if you look at all the neighbors of 6, there's only one neighbor which is 5, which is already explode. Right? So you're not going to make any more recursive calls. What this means is you're going to go back to the previous recursive call. So you go back, you add the edge from 5 to 6, then you go back to 5. Right? So now you're at a stage where you have looked at 2, 4, 5, and 6. They are all explode. The only vertex that's not yet explode is 3. So you go to 3, and now you add this edge from 5 to 3. Okay? Because again, you went to 3 via the recursive call to 5. Okay? And again, now the 2 neighbors that are not explode are 7 and 8. So you mark 3 as explode, you go to 8, you add the edge from 3 to 8, you explode that, you go to 7, you add that edge, and that's explode. So now, at this stage, once you're done with 7, all of the neighbors of 7's explode. So you're going back to the previous recursive call, which is 8. All neighbors of 8 have been explode, so you go back. So you just keep on stepping back through your recursive calls till you're at 1, and this was the original recursive call. You have marked all the neighbors of 1 as explode, and then you're done. Okay. All right, so now talk to your neighbors for half a minute. Let me know if any questions. If not, convince yourselves that the DFS algorithm is indeed a special case of the explore algorithm we looked at last time. All right, any questions? Everyone okay? Oh, sorry, I have to ask your name. Sorry? Wade? Are you asking how am I choosing which of the neighbors I'm picking? So the question was, how am I picking which neighbors I'm picking? I don't remember what I did when I was making the slide. So it's arbitrary. And the definition of the DFS doesn't specify how you're going to do it. Once we start looking at how we represent graphs, in particular adjacency lists, then that typically determines how you're going to access them. Any other questions? Is everyone okay with this being a special case of the explore algorithm? Okay, so just to be sure, what would be the set R at any point of time in DFS? So remember, the explorer would have the set R that's building up as you go along. So if this is a special case of explore, what is set R at any point of time? Is the question clear? Alex.
R would be 1, but also because it's recursive, there would sort of be a new R in every iteration.
Right, that is correct. But what I'm asking is, based on this algorithm definition, if I were asked you to define what R would be based on how the algorithm is defined, how would you define the set R? What set of vertices would be in R at any point of time? I have to ask your name. Okay. Right, so at any point of time, the set R is the set of vertices that have been marked as explored. Okay. All right, and that's why this is, so if you just follow that definition and then you think through it, this shows that this is a special case of the explore algorithm, and as an added bonus, we get its correctness for free, right? Because we argued last time that the more general explore algorithm will indeed output the connected component of a vertex. So this, I said, is the DFS tree. The other thing you could do is like we did for BFS tree, that we try to add the edges that are not part of the tree but were part of the graph. So if you add the edge between, say, 2 and 5, you notice that you no longer have the nice property that we had for BFS, where every edge was either in the same layer or between 2 consecutive layers. But what you're guaranteed is that every non-tree edge is between a node and its ancestor. So an ancestor just means a parent of, you just apply the parent property a few times. All right, so one of the things that I'm not going to prove, but it's there in the book and it's a good exercise for you to figure out, is the observation that if you look at any 2 vertices S and T, either, and you look at the connected component of S and T, either they are exactly the same or they're completely disjoint. So what this is saying is you can never have 2 connected components that only partially overlap. And the reason for that is if they partially overlap, you can go from anywhere here to anywhere here, right? So then they would kind of collapse into one connected component. So we had looked at an algorithm to compute the connected component of a given vertex, but I can also start talking about all the connected components of a given graph, because again, all connected components are either the same or they're completely disjoint. So in other words, if you look at the connected components, they will partition your vertex sets into potentially smaller sets. Now it is possible that if your original graph itself is connected, then you'll only have one connected component, which is the entire set of vertices. But in general, you can have more. So in particular, here's a graph with 2 connected components. And so what I want you to think with your group for the next half a minute or so is, we already know an algorithm to compute the connected component of a given vertex. How would you, for example, use that to come up with an algorithm to compute all the connected components of a graph? Does the question make sense? All right, so think about it and let me know if you All right, any questions? Okay, if not, any suggestion for an algorithm to solve this more general problem? Matt?
Pick a vertex, compute its connected component, and while there's still vertices that aren't in one of the previous connected components, compute their connected components.
Right, so the idea here is you pick, to begin with, any arbitrary node and compute its connected component, say via BFS. And then check if you've covered all vertices. If you have, then you're obviously done. If not, there has to be some other vertex T that's not in the connected component of S. If there's more than one, pick one arbitrarily, run BFS on that, and basically continue this process till you cannot. So let's kind of quickly go over this via an example. So again, we want to compute all connected components of G. And so here's one example which has 8 vertices in total. Okay, so this is my input graph. How many connected components does this graph have? I have to ask your name. Brendan? 3, right? So this is one connected component, this is one, and so is this, and this is crucial. A vertex that is not connected to any other vertex is by itself its own connected component, because by default we always said a vertex is always connected to itself. Okay? So the number of connected components is 3. And so let's say we pick, say the first vertex we pick is 1, and we run BFS on this. So we'll have 1 in layer 0, 2 in the next layer, 3 in the layer 2, and then what would be the vertex in the last layer? What would be L3? Lloyd, right?
4 and 5.
4 and 5, right? So the neighbors of 3 are 2, 3, 4, and 5, but 2 is already taken, right? And now if you try to build the 4th layer, you are not going to get anything, so you stop, right? And so this is the connected component of 1. So now you have handled 1 to 5, but 6, 7, 8 remain. Let's say you pick 8, right? So you run BFS on 8. So 8 goes into layer 0, but then it stops there because there's no other vertices that are connected to 8. So the connected component of 8 is actually just 8. So let me just write this down. The connected component of 1 is 1, 2, 3, 4, 5. And then the only other vertices that are remaining are 6 or 7. Let's say I pick 7. 7 is in layer 0, then you get 8 in layer 1, and then you stop because there's no other vertices to do. And so connected component of 7 is 7 and, sorry, this should be 6, is 6 and 7. Okay. And now you know that every vertex in the graph has been assigned to some connected component, so you stop. Okay? Oh, oops. Did it make sense? Any questions? Okay, so let's say for whatever reason, because I'm feeling so, I just forbid you to use BFS. If I don't allow you to use BFS, how can you solve this problem? Oh man, sorry. Brandon? Right, so you can run DFS, and indeed you can run any algorithm that computes a connected component. So you can run the explore algorithm in general. Okay? So can use DFS or explore instead of BFS. So in other words, the correctness of this algorithm of computing all connected components, all you need as a black box is any algorithm that given a graph G and some vertex S outputs the connected component of S. So as long as you have that, you can just iteratively use it till you're done. Okay, any questions on this? Otherwise, I'm ready to move on from connectivity algorithms. Okay. So the reading assignment is there's a bunch of other stuff in section 3.2 that talks about these things. So, oops. So do go ahead and read section 3.2. All right, so actually I kind of lied. I said we're going to move on now. We're not going to completely move on. What I meant by that is we're not going to look at more problems or design new algorithms. But one thing you might have noticed that we have not done is analyze the runtime of either BFS or DFS. Okay? So what we want to do is do the runtime analysis of BFS and DFS. That's our next step. How many of you have seen the runtime analysis of the breadth first search before? Okay, anyone seen runtime analysis for depth first search? All right. All right, so we want to do the analysis for DFS or BFS. So as is the case, if you want to do runtime analysis, we now have to design data structures and figure out how to represent with various data structures that are needed in the algorithm. But if we start thinking about that, notice that we have not even talked about how do we represent graphs itself. Right? If I say adjacency lists, to how many of you does that make sense? Okay, adjacency matrix. Okay. Oh, apparently there is a band called BFS too. All right, so what we're going to look at are, to begin with, two data structures that you should have seen so by now, stacks and queues. And stacks is basically a data structure that is, you can think of it as linked list with last in, first out. So you stack things together and take things from top. Or you could have a queue, which is first in, first out. Right? And it turns out that for BFS or DFS, the algorithms are, once you start implementing it, the algorithms are almost the same, except in one place you use stack for DFS, and you use queue for BFS. And in that sense, that's the only thing that's different. Okay? And the reason why that's the case shouldn't be too hard to think about if you just sit down and think about it. Note that both of them are special cases of the explore algorithm, right? So the only thing that they differ is how do you pick the next guy that's outside of your arm, right? And so what the stack or queue does is essentially tell you which is the next guy you should pick. All right, so I said we're going to use stacks and queues for BFS and DFS, but we actually have to at least start off by talking about how do we represent graphs. So I'm not going to formally define adjacency list or adjacency matrix. Again, it's defined in the book, but it's easy enough to start off with an example and then we'll see what they look like. So let's look at this simple graph with 3 vertices and 2 edges, which I've colored them blue, green, and red. Adjacency matrix is a 2-dimensional array or a matrix, which by now, since you're doing homework 3, you should be familiar with. So it's a matrix which is an n cross n matrix. Every row and every column corresponds to one of the n vertices, right? So over here, the first row corresponds to blue, then green, then red, and similarly on the columns. And if you look at, say, this entry which corresponds to the blue node as the row and the green node as the vertex, green node as the column, then you have a 1 in that entry if there is an edge. Right? Put another way, you look at any row, let's say the red one, and any column, which is the green one, you get a pair of vertices, right? So in this case, red and green. And you have 1 in that entry if there is an edge between those two pairs, otherwise you have a 0. Right? So in this case, the only edges that are present are between green and the other two guys, blue and the other two vertices. So if you look at the first row, you have a 0 because in the first, the blue comma blue entry, because we are assuming we don't have any self loops. But then there is an edge to both green and red. And similarly, green and red have the edge to the blue vertex. Right? But everything else is 0 because there is no edge, say, between green and red. Are there any questions on this? Does this make sense? Alright, the other representation is called adjacency lists, and it turns out if your graph doesn't have too many edges, for example, if your graph is a tree, then this is a good data structure to use. And what you have over here is an array of lists. So you have an array where you have 1 entry for each of the vertices, so blue, green, and red. And each entry points to a linked list that corresponds to its neighbors. Right? So the neighbors of blue are green and red. Again, neighbor means there's an edge between blue and green and blue and red. So the entry corresponding to blue points to a linked list which has red and blue, red and green, or green and red in it. Similarly, if you look at the adjacency lists or neighbors of green and red, it will just have one guy which is blue. And I forgot who asked that question, but for example, if you're doing DFS using this data structure, typically the order in which you're going to go through, the order in which you're going to walk through the neighbors or the edges depends on the order of this list. All right, so given this, any questions on, before we go on either adjacency matrix or adjacency list? Okay. All right, so if not, let's, we want to look at certain queries that would want to do these data structures. So let's say I give you two vertices U and V, and I ask you whether there's an edge between U and V. How much time would it take to figure that out in the adjacency matrix representation? Alex? Oh, 1. You're just looking at one entry in the matrix, right? So you just look at, say, row U and column V, and that entry, just read that entry. Okay. How much time would it take it in the adjacency list format? I have to ask your name. Sam. In the worst case, it's O of n, right? Because it could be possible. So again, the idea here is, let's say I want to look at, whether there is a green and red present. So I'll go to the, blue and red. Is there an edge between them? So I'll go to the adjacency list of blue and walk through the list, which in the worst case could be all of them, right? So in the worst case, it's O of n. But it turns out, and it might not be apparent why I'm nitpicking here at this point of time. But for example, if you're looking at the adjacency list of V, and there are NV of the neighbors, then it's order n of V, right? So all I'm saying is O of n is a correct upper bound, but you can do slightly better by saying what is my list size, or how many neighbors does V have, and that's a valid upper bound. And we'll see shortly why doing this actually is useful when we are doing runtime analysis and stuff like that. All right, let's say now if instead of checking whether U has an edge to V, what if I wanted to know all the neighbors of V? So the input to the query is just one vertex U, and you have to output the list of all the neighbors of U. How much time would that take with the adjacency matrix? This is bad. Brandon? Yeah, okay.
All of that.
O of n, right? Because even if, for example, that has only one neighbor, you will not know till you kind of walk through the entire row, right? So for example, if you wanted to know all the neighbors of red, you say, aha, blue is one, so blue is a neighbor. But unless I go and check this entry for the green guy, I won't know for sure whether green is a neighbor or not. So in the worst case, you pick a vertex U, you look at its entire row, and that will take order n time. Right? In fact, it's theta n. All right, how much time would it take in the adjacency list format? Lloyd.
It's going to be O of 1 if you store the edges in arrays.
No, so you are stored, this is the representation. You're not changing your representation. What is the time in this representation to get all neighbors of U? Matt? Right, so the point is what you have to do is you actually have it already there, right? So it's there in the linked list corresponding to U. So you just have to walk through the list. So O of NU. Okay, so it's slightly better. All right, the other thing which is important in graphs is how much space does it need, right? Of course, we care about time, but space is also important. Again, think of n as being million, and so the question is, you want to figure out whether these data structures are, even if it's possible to store these big graphs. So how much space would the adjacency matrix require? How many entries do you need? Yeah, so as Steven just said, it's n squared, right? There are n squared entries in the matrix, so you need one. Okay, good. Any guesses for space for the adjacency list? And say? Sorry? Answers guesses log n. That's generally not possible. So for example, if your graph, in the worst case, that's not true. Any other? Megan, right? N squared. So O of n squared is definitely a valid thing. Why? Well, in the worst case, you could have these lists all of size n, right? So for example, if your graph is what's known as a clique, that is every vertex is connected to everything else, then you have size n squared. But it turns out you can actually do something better, especially if your graph has very few edges. So if your graph is a tree, and so m is like only n minus 1, then you can store everything in order n space. And more generally, you can store it in order m plus n space. Okay. And so we'll see why this is the case. And the fact that you can store each list in size O order n of U is going to be important for this. So if your graph is sparse, i.e. the number of edges is, say, comparable to n, which tends to happen for most real-life graphs, then adjacency list is the way to go. So what that means is, if, say, Google is dealing with graphs, you can bet your whatever you want to bet on that they're not using an adjacency matrix, right? Because the graphs are huge. They're actually probably not even using adjacency list, but definitely not adjacency matrix. All right, so what we're going to prove is a very neat fact that, among others, will allow us to prove that the space required for adjacency list is order m plus n. And here's the identity. It says twice the number of edges is exactly equal to sum of number of neighbors of all vertices. So a bit more mathematically, the number of edges is 2m, and that's saying that the quantity 2m is exactly equal to the sum over all vertices u of the number of neighbors of u, which is n of u. Okay? Is the statement clear? All right, so actually let's prove the statement. It's not that hard to do, but it's a cute way to argue this. So what I'm going to do is, I'm going to do this mental exercise where I'm going to give each edge 2 pennies. Okay? So each edge gets 2 pennies. So for example, if you have the edge UV, then it gets 2 pennies. And then what you do is the edges are really generous. They take the 2 pennies and give them 1 to each of their endpoints. Okay? So, oh, by the way, sorry, before, since every edge got 2 pennies, the total number of pennies is 2m, right? M edges, each edge gets 2 pennies. So you've handed out a total of 2m pennies. Okay? Now I said what's going to do, every edge is going to has 2 pennies and it's going to has 2 endpoints, 2 vertices. It's going to give 1 penny to one endpoint, the other penny to the other endpoint. So for example, all of these edges get 1 penny each, and then the pennies get pushed to the nodes. The important point to note is, or let me ask this as a question, how many pennies would a vertex U get? Richard.
All the number of neighbors they have.
Right, it's the number of neighbors, right? Because it's getting 1 penny from each of its edge, right? And in particular, as we have already defined it, the number of neighbors is exactly n of u. Okay? So I started off with handing out 2m pennies to the edges. They pushed all the pennies to their endpoints. And so if you look at the sum of the pennies that all the nodes have after this, is actually exactly this sum. It's sum over u of the neighbors of u. Okay? And this is like basic finance. Like if you have 2m amounts of penny and handing out stuff and you're not doing any hocus pocus, then at the end you will still have the same amount of pennies. Right? So you started off with 2m pennies, you handed them out, and you realize the total number of pennies that you have is sum over u of n of u. So these 2 quantities have to be the same. And so that's the proof. Why don't you talk to your neighbors for half a minute? Let me know if any questions. If not, we'll move on. All right, are there any questions on this proof? Or anything we have seen so far? So everyone okay with the identity that 2 of m is exactly equal to the sum of number of neighbors of each vertex? Okay, so what we're going to do next is use this identity to argue that the space requirement for the adjacency list representation is order m plus n. So again, as a reminder, n of u is the number of neighbors of u. It's also in literature called the degree of u. So it's like you have vertex u and you have a bunch of guys going out. It's the maximum number of, it's the number of guys that's going out. So as I said, we just proved that 2 of m is sum of u of nu. To be more precise, is sum over all vertices u. And so now let's look at an adjacency list. I have a list of pointers to linked lists, and so for example, I have one entry for each vertex u, and then it has its list of neighbors, say in a linked list. Again, how many entries would be there in this linked list? Ask your name. Sorry, did you say NU? Yeah. Who? NU, right? So what you have as the list for u is the adjacency list, that's the list of all neighbors, which by definition is of size n of u, right? We just said n of u is the number of neighbors. Good. So the list for u is of size nu. So now let's look at the space. So we have to store some pointers, and in particular we have n pointers or n locations in the array. And the only other space that you need is to store all of these lists, right? So the sum of list sizes is sum over u of n of u, because vertex u has a list of size n of u. Okay. And this we already seen is exactly 2 of m. So that implies overall we need n plus 2m entries, which is order m plus n. Okay? And so this is why it was useful to be a bit more careful, and you said when you're looking at the size of the list of a vertex u, you could have said it's O of n, and that would be a valid upper bound. But bounding it by O of nu or exactly nu allows you to have this slightly better estimate. And so the question is, how good is this in general, right? So just to be sure, so m can be, of course, be as small as 0, which is the case where there are no edges. So your graph, if you draw them out, is just a bunch of n dots. Right? But how large can m be in terms of n? What is the maximum number of edges you can have in an undirected graph with n nodes? Forgot your name. Jared. You can have more than n minus 1 vertices, edges in the worst case. So think of the case when the adjacency matrix, all the entries are 1. Right? You have all possible pairs have edges. So n squared is a valid upper bound. If you are a bit more careful and think about it, and you can do that at home, you can show that it's at most n choose 2, which is n times n minus 1 over 2. All right, so what this says is this can, on the one end, be as small as O of n, in which case this is great. You're saving a lot of space over the adjacency matrix. Or it can be as large as O of n squared, in which case it's probably not clear why you would like to have an adjacency list. And so in this case, adjacency matrix is probably better. Any questions on this? And it turns out for pretty much all the algorithms based on graphs that we're going to do in this course, adjacency list is the way to go. So that's going to be our de facto data structure. So for example, if in the homework you get a question saying you're given a graph, you should assume by default, unless it's specified otherwise, that it's given to you in the adjacency list format. Okay? All right, so finally, we are now ready. So we have all the data structures that we wanted in place to now talk about analyzing the runtime of the Dfs algorithm. And the way we're going to do it is follow the lead of the book and kind of give you two instantiations of how you can implement it. So if you notice, remember the way we're looking at BFS is you're building these layers one by one, right? So you start off with L0 being the sort layers, and then you have L0. You build list from L0 to Lj, and then you build the next layer L of j plus 1. So one of the easiest way to do this is just have one linked list for each layer. So whenever you're building it up. And to keep track of whether a node has been chosen yet or not, instead of going through and looking through all lists, which can be bad, you just keep a Boolean array that for a given vertex v tells you whether it's already chosen in one of the layers or not. And it turns out, we're not going to focus too much on this, but you can read up in the book, you don't even need to have, instead of having different layers, so if you think about it, how are you doing it? You're doing L0 first, then L1, then L2, then L3, right? So the way you are accessing the vertices is starting with L0, then vertices in L1, then vertices in L2, and so on and so forth. So you can in fact have one data structure that handles all of this, which is just use a queue, but because you're going in that order. So here's an illustration of the BFS where instead of having different layers, I'm just going to have a queue to put everything in there. So the way I'm going to do this, I'm going to start off with 1, and I'm going to put it in my queue. Okay, so that's what I start off with because that's my start vertex. And the way the BFS algorithm will done is pull from the front of the queue, which is 1, take it out, and then put in all the neighbors of 1 that have not been seen yet back into the queue, right? So in this case, 2 and 3 are the neighbors, and you put those into the queue. Again, you pull from the front of the queue, which in this case would be 2. And then, so just to be sure here, the neighbors of 2 are 3, 4, and 5, but you do not put 3 in because it's already visited or it's already been explored. Right? So you put in 4 and 5 at the end. Then you go in the front of the queue, that's 3, so you pull out 3. Neighbors are 1, 5, 7, 8, but you're not going to put 1 and 5 because they're already being seen. So you're going to put 7 and 8 at the end. So then you're going to pull out 4. There's nothing interesting happening here. You stop. You pull out 5. And now you have a neighbor which is 6 that's not explored. So you put 6 back in. And then basically you just pull guys out one by one. And once your queue is empty, you're done. Okay. So instead of having different linked lists for different layers, you basically have one linked list which you do as a queue. And the way you do it is pull out from the front of the queue, and towards the end of the queue, put in all the neighbors of that vertex that you've not already seen. Okay? And it'll probably take a bit of thought, so go back and think about it, but you can convince yourself that this will behave exactly like how we talked about doing the layers earlier. Okay? All right, sorry for running over a bit on time. I'll see you guys on Friday.